Yo, what's up guys? Welcome to another episode of Stonks Maxxing. We made it to day 40, so very exciting. And today, just want to go over micron technologies. I think this might not be part 1, but maybe part 2 or 3. I just forgot the number, so I started it back at part 1 for now. Maybe change the name later. But Micron Technologies is one of the companies that's within the Symbit fund. So that's the fund that I'm currently, I guess you could say, volunteering for my school. And there's about 3 different companies that I cover: Apple, Micron, and Cisco. So this one, Micron, I feel like is going to be an interesting company to look at. It's a direct beneficiary of the CHIPS Act that was enacted about 2 years ago, I think in 2022. And recently it got funding, I want to say back in April of 2024, for either 1 or 2 new foundries for memory chip production. So memory is the idea of a chip, really, or semiconductor that can store short-term temporary data for some type of electronic device to use. And this is also very similar to the idea of storage. So storage is more permanent memory. So it's really long-term permanent storage that you want to be able to keep your data indefinitely. So there's 2 slight differences. One is short-term, which is memory. One is long-term, which is storage. So memory, there's a common term, or maybe products, I guess. Is dynamic random access memory a technology? Is it a product? Is it a name with no meaning? I don't exactly know, but I think it is a type of product, a type of memory that is short term. So random access memory, RAM, is, I believe, accessed by the CPU, the central processing unit of a computer. And so all logical chips, I think not only CPUs, but also GPUs. So any logical unit or any processing unit is going to need to store data somehow, right? So I think maybe a good explanation of this could be, let's say that your CPU is running on the x86 instruction set. So I think what that means is there's a certain set of instructions that the CPU can actually handle. And so one of this instruction could be adding 2 bits together. And so in order to actually add those 2 bits together, you need to have a single bit and another bit. And how do you even, I guess, get that bit, or how do you use that bit for an addition operation? You need to store that somewhere, and you store that in memory. And I think how that works is you have these things called registers, which could be very small transistors or maybe pockets of copper. I don't exactly know, so that could be an interesting thing to go into. But yeah, I think you're just storing them on these little chips. This is an example of RAM, I believe. Let's see if we can get a little bit deeper to this. But we also have NAND. So NAND, I think, is flash memory. Solid state drives, this is SSD. This is SSD storage. Yeah. NOR, I'm not entirely sure. But let's go into DRAM. What is DRAM? Yeah, maybe this is a worthy YouTube video watching. Oh man, it's left. Interesting. So,
have you ever wondered what's happening inside your computer when you load a program or video?
Inside the smartphone
Well,
are
millions of
62
operations are happening. But perhaps the most common is
Oh, wow.
simply just copying data
Say
from a
that.
solid-state drive or SSD into dynamic random access memory or DRAM. An SSD stores all the programs and data for long-term storage, but when your computer wants to use that data, it has to first move the SSD. Have you ever wondered what's happening inside your computer when you load a program or video game? Well, millions of operations are happening, but perhaps the most common is simply just copying data from a SSD into dynamic random access memory or DRAM. SSD into dynamic.
Okay, yeah, this is actually a pretty interesting diagram to have here. So it could be worthy of adding down. Alright, let's see. What is... Oops. This picture reps moving data from storage SSD to memory DRAM. Okay.
Memory or DRAM. An SSD stores all the programs and data for long-term storage, but when your computer wants to use that data, it has to first move the appropriate files into DRAM, which takes time, hence the loading bar. Because your CPU works only with data after it's been moved to DRAM, it's also called working memory or main memory.
Okay. So DRAM is also known as main memory or working memory because it is the data that is used by the CPU to complete instructions.
The reason why your desktop uses both SSDs and DRAM is because solid-state drives permanently store data in massive 3D arrays composed of 1 trillion or so memory cells, yielding terabytes of storage, whereas DRAM temporarily stores data in 2D arrays composed of billions of tiny capacitor memory cells, yielding gigabytes of working memory.
You know, that's actually a very how do I say this?
Temporarily stores data in
Very
2D
clear
arrays composed of billions of tiny capacitor
animation.
memory cells, yielding gigabytes of working memory.
Yeah, let me...
Accessing any section of cells in the massive SSD array and reading or writing data takes about 50 microseconds, whereas reading or writing from any DRAM capacitor memory cell takes about 17 nanoseconds, which is 3,000 times faster. For comparison, a supersonic jet
Okay, so this picture represents how DRAM and SSD are structurally different. So what is a memory cell? structurally different with different amounts of... Oh, wait a minute. So terabyte, trillion bytes, which is a byte is a sequence of 8 bits, right? So if you have a trillion bytes, that means you have 8 trillion, a sequence of 8 trillion bits. Let's see. How many memory cells does a 1 TB terabyte SSD have? Oh my god. Or they eventually leak off over the course of a decade or more. A three-dimensional array of transistors. So I'm not entirely sure what that means, a three-dimensional array of transistor. I guess, okay, maybe I do. It's just like a cube, right? A cube, or in this case, a rectangle of transistors. Yeah, so there's some stuff here I don't fully understand. So this is not a digital circuit. Okay, if I remember correctly, a digital circuit just means that you have two discrete, or maybe not necessarily two, but at least a discrete set of signals that can be passed through the circuit. While analog can be continuous. So you can have really anything being passed through. Now, how does that actually look? I'm not entirely sure. Okay, so yeah, this is interesting. I'm gonna save this, maybe come back to it. There's a bit of some interesting stuff here, but it's a bit too technical for me. SSD and their transistors work. Memory cells. Okay, so I think at a high level then, six transistor SRAM memory cell. So a memory cell is a circuit. So I think if we define circuit again, going back to the basics, I think all it is, it's a connection of different components. It includes wires, maybe even transistors, capacitors, amplifiers. Now, I don't know exactly what those mean. I just know, I think transistors are a type of switch, so they allow you to, how should I say this? They allow you to either stop or allow the flow of electricity. And then I think maybe capacitors allows you to take a single flow of electricity and then break it off into two pieces and allow them to keep going. I want to say that's the case. Could be wrong. Memory cell is an electronic circuit that stores one bit of binary information and must set to store logic 1, high voltage levels, reset to store logic 0. Metal oxide semiconductor memory cells. Oh, MOSFET. Well, I think these are analog transistors, right? That's what we saw last time. So they could take in a continuous signal. Okay, so RAM exists in most modern computers today. Let me see. Memory cell is a circuit that is able to, I think, represent or store 1 bit of binary information. See, I guess it'll
Going
keep
at
going.
Mach 3 is around 3,000 times faster.
Oh, right. So DRAM is a lot faster than SSD.
Than a moving tortoise. So the speed of is around 3,000 times in a supersonic jet going at Mach 3 is around 3,000 times faster than a moving tortoise. So the speed of 17 nanosecond DRAM versus 50 microsecond SSD is like comparing a supersonic jet to a tortoise. However, speed is just one factor. DRAM is limited to a 2D array and temporarily stores 1 bit per memory cell. For example, this stick of DRAM with 8 chips holds 16 gigabytes of data.
So each chip can maybe store 2 gigabytes.
Whereas a solid-state drive of a smaller size can hold 2 terabytes of data, more than 100 times that of DRAM. Additionally, DRAM requires power to continuously store and refresh the data held in its capacitors. Therefore, computers use both SSDs and DRAM, and by spending a few seconds of loading time to copy data from the SSD to the DRAM, and then prefetching, which is the process of moving data before it's needed, your computer can store terabytes of data on the SSD and then access the data from programs that were preemptively copied into the DRAM in a few nanoseconds.
Yeah, this is kind of groundbreaking.
Many video games have a loading time to start up the game itself, and then a separate loading time to load a save file. During the process of loading into copies and DRAM, and by spending a few seconds and refresh megabytes of data, this stick of D temporarily stores 1 bit.
Yeah, so this is an interesting diagram of a memory cell. I'm gonna copy and paste this. So this is with DRAM memory cell. Oh, so is this might be the MOSFET thing. Okay, I think this is starting to make a little bit more sense. So if you have this, I guess this is a 3D array of, or really a 2D array, right? Because you're not stacking them on top of each other. More so you're stacking them next to each other. But you have this structure of, let's see, MOSFETs. I think this is a transistor. Metal oxide semiconductor field effect transistor. So this, okay, this might be the actual MOSFET transistor, and then I think maybe, so this bit could be a, okay, what is this storage capacitor? Capacitor. Okay, never mind then. I totally do not know what a capacitor is. I said something that allowed signals to switch, but no, capacitors are things that store electrical energy. So this is interesting then. I think this is starting to come together a little bit. So this could be the MOSFET transistor that allows electricity to flow into or in and out of the electrical capacitor. And so this electrical capacitor will store that bit, which is represented by the amount of electricity. And you know, now that you think about it, the people who thought of this are geniuses. How do you even think about any of this stuff? How do you even know how to capture electricity? I'm 22 and I would have never thought about doing this at all. I mean, I don't even know how to start. Without the internet, without anything, any textbooks or nothing. I mean, how the hell do you even understand any of this? Okay, but getting ahead of ourselves. So with DRAM, so DRAM stores data using a memory cell that is made up. So today call this 2024. DRAM stores data using a memory cell that is made up of a MOSFET so this is a oxide semiconductor field effect transistor and storage capacitor. Yeah, let me see what time it is. Okay, so storage capacitor, right. So a capacitor is a device that stores electrical energy. Let's take a look. Fixed capacitor, polarized capacitor, variable capacitor. I don't know what these fancy little squiggles are. Oh, I think we talked about terminals too last time. So terminals, I want to guess, it's a way that you can interact with the circuit. You have two terminals, meaning that you have two maybe points in which your capacitor interacts with a circuit. Let's see. Is the point at which a conductor from a component, device, or network comes to an end. Point acting as a reusable interface to a conductor. Okay, yeah, I was totally off. Hey, worth a try though. So might need to go back to that a little bit later. The utility of a capacitor depends on its capacitance, while some capacitance okay. So if you take the integral of C, yeah, I'm not entirely sure what these symbols mean. So I'd assume maybe then if we're working with integrals, so these are all analog in the sense that they are able to store signals that are not just 0 or 1. Master in chemical engineering. Johns Hopkins. wow. Okay. Okay, yeah, I was just thinking about some random stuff, so that kind of caused me to get off task, but let's try to see. A capacitor is a device that stores electrical energy. Let's add a picture. Hey, what does a bipolar mean? Storage capacitor. So it's a battery, right? Dielectric material. So maybe a good question is, what is electricity? Is it some type of energy? A form of energy? Oh, right, just electrons resulting from the existence of... That's cool, that's cool. Is an electrical insulator that can be polarized, which refers to the tendency of a matter when subject to an electric field to acquire an electric dipole moment in proportion to that applied field. No idea what that means. It's a property of a particle with an electric charge. Yeah, so I'm gonna hold off on this for now. We're going into pretty deep technical territory, so I'm gonna say this, that maybe MOSFET will be interesting here. A MOSFET transistor is a type of transistor that it's a field effect transistor. So FET, I think, was something invented by Intel. Field effects transistor. So FinFET, I think, is also another thing. which is an electric field. Yeah, this thing looks so confusing. I've seen this so many times on Wikipedia, but I can never understand what this is talking about. Like, what does this even mean? Electromagnetism. So magnets, I know opposites attract, that's about it. A magnetic field. Oh, so maybe that has to do with charge. And I think charge has to do with the number of electrons that you have. I don't know exactly what else from that we can get. Okay, which is a transistor that has a source, gate, and drain terminal. Okay. I'm getting kind of tired, so yeah.
Per memory cell. For example, this stick of DRAM with 8 chips holds 16 gigabytes of data, whereas a solid-state drive of a smaller size can hold 2 terabytes of data, more than 100 times that of DRAM. Additionally, DRAM requires power to continuously store and refresh the data held in its capacitors. Therefore, computers use both SSDs and DRAM. And by spending a few seconds of loading time to copy data from the SSD to the DRAM, and then prefetching, which is the process of moving data before it's needed, your computer...
Okay, so let me actually add that. Prefetching refers to the process of moving data before it is needed. So where does prefetching into a cache? So I guess a cache is just where you store data that's going to be used later.
Computer can store terabytes of data on the SSD and then access the data from programs that were preemptively copied into the DRAM in a few nanoseconds. For example, many video games have a loading time to start up the game itself, and then a separate loading time to load a save file. During the process of loading a save file, all the 3D models, textures, and the environment of your game state are moved from the SSD into DRAM, so any of it can be accessed in a few nanoseconds, which is why video games have DRAM capacity requirements. Just imagine, without DRAM, playing a game would be 3,000 times slower. We covered solid-state drives in other videos, so in this video we're going to take a deep dive into the 16 gig...
Okay, so this is a really good example of loading in a video. Video game example. So, yeah. When we are playing a PC game, let's say GTA 5, the game files are all stored in SSD, long-term storage. So we have our textures, config files,
store terabytes of data on the SSD and then access the data from programs that were preemptively copied into the DRAM in a few nanoseconds. For example, many video games have a loading time to start up the game itself, and then a separate loading time to load a save file. During the process of loading a save file, all the 3D models, textures, and the environment of your game state.
So, 3D models. The game files and these software are all stored SSD. Long-term storage. That's why whenever we are playing, that's why when we start a game, initially open the game up, it takes a few seconds because the computer is moving data from SSD to DRAM. Yeah, that is actually really, really interesting. So, GTA 5. There are also save files that are being loaded into DRAM as well. So this is 3D models, textures, and config files.
Are moved from the SSD into DRAM, so any of it can be accessed in a few nanoseconds, which is why video games have DRAM capacity requirements.
Yeah, it's interesting. So DRAM capacity is super important for running video games quickly because it allows you to store more data that can be accessed a lot quicker than SSD. Oh. Stream's current bitrate is struggling for some reason. Don't know exactly what that means. Hope it's okay. DRAM's capacity is super important for running video games because it allows you to store more data that can I think frames per second is how quickly or how fast your game can render a new frame or a new frame as you're making a movement, right? With higher RAM, yeah, DRAM capacity, a video game can run much smoother at a higher FPS because it is able to load new data, so textures, models, much faster. Right. So, how do you kind of explain this? It's like a mother-son relationship. Like your solid state, your SSD, your solid state drive is an old and wise person, and it gives information to the younger but less wise but more motivated dynamic random access memory. And in the case of video games, this younger DRAM is able to process data a lot more quicker, which allows you to run your computer games a lot faster. Yeah. I'd say it's okay. Let me take a look real quick. Yeah, I'm gonna go take a bathroom break real quick. Come back. Alright. Let's keep going.
Just imagine, without DRAM, playing a game would be 3,000 times slower. We covered solid-state drives in
Okay, never
other
mind. I gotta
videos.
get this
So in
call real quick. I'll be back in a sec. Yo. Okay, I'm back. I was just trying to set some things up to meet my friends out in Virginia. They're biking across the US, so want to go support.
In this video, we're going to take a deep dive into this 16 gigabyte stick of DRAM. First, we'll see exactly how the stick drives and be 3,000 times slower. We covered solid-state drives in other videos, so in this video we're going to take a deep dive into this 16 gigabyte stick of DRAM. First, we'll see exactly how the CPU communicates and moves data from an SSD to DRAM. Then we'll open up a DRAM microchip and see how billions of memory cells are organized into banks, and how data is written to and read from groups of memory cells. In the process, we'll dive into the nanoscopic structures inside individual memory cells and see how each capacitor physically stores one bit of data. Finally, we'll explore some breakthroughs and optimizations, such as the burst buffer and folded DRAM layouts that enable DRAM to move data around at incredible speeds. A few quick notes. First, you can find similar DRAM chips inside GPUs, smartphones, and many other devices, but with different optimizations. As examples, GPU DRAM, or VRAM, located all around the GPU chip, has a larger bandwidth and can read and write simultaneously, but operates at a lower frequency. And DRAM in your smartphone is stacked on top of the CPU and is optimized for smaller packaging and lower power consumption. Second, this video is sponsored by Crucial. Although they gave me this stick of DRAM to model and use in the video, the content was independently researched and not influenced by them.
Hey, shut up, micron.
There are faster memory structures in your CPU called cache memory, and even faster registers. All these types of memory create a mem. Third, there are faster memory structures in your CPU called cache memory.
Okay. So cache memory. I guess these are the registers, so cache memory is used by the CPU, is stored in the CPU and
even faster registers. All these types of memory create a memory hierarchy, with the main trade-off being speed versus capacity. Create a memory and even faster registers.
oops. It's even faster than DRAM. Okay. There is a hierarchical, I butchered that, hierarchical structure to memory in which higher where higher speed memory is often treated as a trade-off of lower capacity, less data storage abilities.
All these types of memory
Data, I guess in this case, is just represented as bits, so it's just 0 and 1.
create a memory hierarchy, with the main trade-off being speed versus capacity, while keeping prices affordable to consumers and optimizing the size of each microchip for manufacturing. Fourth, you can see how much of your DRAM is being utilized by each program by opening your computer's resource monitor and clicking on memory. Fifth,
Okay, wait, can we do that here? About this Mac. Let's see, how to monitor DRAM usage on Mac. Activity monitor. Physical memory, app memory, cache files. I guess physical memory here is referring to DRAM. All right. Let's take a look. Yeah, I'd assume probably so. And then storage, I think, is probably different. CPU. So we have 2,600 or so threads. I think threads exist or stem from a process. A process is just some type of instruction, some type of software that's running, maybe. Energy, battery, disk, data read, read-ins, read out. I think disk is referring to the solid state drive, possibly. Network, I don't know. Okay, I guess this is referring to the network that we're currently connected to, which is my internet connection. It's provided by, I think, Verizon. So my Wi-Fi, man, I think I was going over this yesterday, right? So Wi-Fi is a standard actually, and it's a way of sending data through a network. I think that network is supported by a router, and that router then is connected to either physical cables or could also be connected through cellular networks, which is a fixed area net. FWN, fixed wide network, or FWA, fixed wide area network. Okay. Kernel task. Yeah.
There are different generations of DRAM.
Let me see actually. TV monitor. So these are all process names. UTC, Watchdog, Apple. So these are all Apple. Actually, no, they're not. Right? Watchdog D. Advanced System Monitor and Process Supervisor for Linux or Linux. Yeah. Oh, Intel. So I guess a driver is something that allows you to connect or allows you to use certain types of hardware, I'd assume.
And we'll explore DDR5. Many of the key concepts that we explain apply to prior generations, although the numbers may be different. 6th, 17 nanosecond DDR5. Many of the key concepts of Shooter's Resource Monitor and clicking on memory. 5th, there are different generations of DRAM, and we'll explore DDR5. Many of
Okay, so there are many generations of DRAM. Today it is DDR5.
The key concepts that we explain apply to prior generations, although the numbers may be different. 6th, 17 nanoseconds is incredibly fast. Electricity travels at around 1 foot per nanosecond, and 17 nanoseconds is about the time it takes for light to travel across a room. Finally, this video is rather long, as it covers a lot of what there is to know around DRAM.
Okay. Maybe I'll add this here. So DRAM is able to be transfers is read / written. Maybe this. It takes a CPU today around 17 nanoseconds to read / write from DRAM. 17 nanoseconds is fast as fuck. Video gave an example where saying that's about the same as light traveling through room. Light travels a foot per nanosecond. I think a nanosecond is a thousandth. How fast is a nano? No, it's 1/1000th of a second. A nano. Oh, milliseconds probably a thousandth. What's a? Okay. Second is 1/1000th of a second. That's, I think, eight zeros before? Or is it 9? Yeah, it should be eight zeros. So it's be 9 minus 1, 8 zeros. Behind the decimal. Oh, right, because it's a 10th. Okay. Yeah, man, that is really, really fast. I did not know nanosecond is 1/100000th. I thought it was more of a thousandth. But I'm gonna save this here. So this is a very exciting video to watch. I think it will be really interesting to see what's gonna happen and what we can learn about in the future. So I'm going to branch education. How does computer memory work? So this is pretty new too, just about a year ago. Okay, I'm gonna, oh wow.
Empower your students at every stage of the writing process with Grammarly's generative AI.
Inside the smartphone are 62 microchips containing a total of 9.
How do hard drive? Okay, this could be interesting for watching as I'm trying to build my own PC right now. So yeah, that would be pretty cool. How does Bluetooth work? Oh man. Yeah, this could be fire too. Okay, I feel like this guy, Harvard University, yeah, I could tell he's from Cambridge. Applied materials. Oh, right. Oh, okay, Harvard Extension School. Winchester, I don't know where that is actually. But applied materials. I feel like that, yeah, they're chip manufacturing company. I think they have a stock, right? Yeah. as a massive multi-layer labyrinth with walls just 13 nanometers wide, 20 or so floors tall, and the overall size of your thumbnail. The bottom 5 floors of the labyrinth-like microchip are built by using a stencil spray paint. The stencil is a stepper tool, garage size, and costs 50 million. Oh man, it uses photolithography while the spray paint is an ion implanter garage. Okay, so yeah, what is it called? Ion implanters. Let's see. Oh, okay. So this seems like this is used for doping. Yeah, I don't know exactly how that works, but I guess his video on, I'd assume his video on semiconductor manufacturing is probably going to help. Ooh, touchscreens displays. What is sound? Yeah, these could be all interesting videos to watch. Ooh, compression. Yeah, it's cool. Okay, so with that, I'm gonna probably call this here, and I'll catch you guys in the next one. Thanks for tuning in. This was a very interesting channel and a very interesting video, so I'm excited to see what else he has here. Yeah, catch you guys in the next one. Peace.